In this video, we'll look at the concept of negative numbers in binary. In previous videos, we've looked at the concept of positional numbers systems in general and focused on binary. We've counted a bit in binary to get a feel for how the digits tick over, and we've converted numbers back and forth between the binary representation and decimal, which we are more familiar with. Let's have a look at the example that we did in the previous video, 1429. I'm fairly confident that with our new knowledge we could write just about any positive integer in binary. But what happens if we need a negative number? Well, if we were mathematicians in the 19th century, we'd just make a little mark on our paper indicating that the number is negative, and that would be that. Not a very interesting topic. For electronics though, this isn't very useful. Rather than ink on paper, digital circuits store the numbers that they work with in some sort of memory with a fixed amount of spaces for storing binary digits or bits. For the purposes of this discussion, let's assume that we have 16 bits available, a fairly common size. In our example, the first 5 bits aren't used, so we'll pad them out with zeros. Adding 0 to the beginning of a number doesn't change its value, so we can do that. We could potentially use one of these bits to represent a sign. Let's make the number negative by putting a 1 in the leftmost or the most significant bit. The rest of the bits we already know to represent 1429 in binary. This notation is similar to putting a minus on the left-hand side of the number on our paper, and it's quite simple for a human being to understand. However, it is more complicated for machines. For example, you wouldn't be able to naively add this negative number to a positive one. Your system would have to note that one of the numbers is negative, compare which of the numbers is greater in order to determine the sign of the result, and then subtract the two numbers. All the circuitry necessary to do this would need to be designed and integrated into the system, adding to its cost and its complexity. So we're not off to a great start. Another way to represent negative numbers is through the method of complements. Various such systems exist, but the principle with all of them is the same. A number added to its negative or complement should equal 0. Advantages of this method include a simple negation operation, which works in both directions, and the same circuitry can be used for both addition and for subtraction. Two's complement is the system utilized in almost all modern electronics. It's an example of a radix complement system, the word radix being a more technical term for the base of the number system, in this case 2. Negating a number works by reversing all the bits and then by adding 1. Let's look at the example. Starting with our previous example padded out to 16 bits. The first step is to reverse all the digits, including the zeros which we padded out. Those become 1s. Then we add 1. There's a very simple trick involved here which isn't revealed so easily in this particular example, so let's use another one as well. If we consider the number 12 in binary, using only 8 bits this time because it's a smaller number, we don't need all 16, and apply the same steps as previous. Invert the bits and add 1. We notice that the 3 rightmost bits, the least significant bits, are the same in the negative and in the positive representation. It turns out that this trick is generally true. In the negative representation of any number in 2's complement, the lowest or least significant bits up to and including the first 1 remain the same, and all the higher or more significant bits are inverted. If we have another look at the first example, we see that this is still true, except in this case, the very lowest bit is 1, so that 1 stays the same, and every other bit is flipped. As I mentioned previously, this method also works to negate a negative number, or to get the positive number back. There are no differences. You don't even need to know whether you're working with a negative or a positive number. You just need to use the defined number of bits, and the same mathematics applies. Take some time and try this out for yourself with the 2 examples that we've done, or make some of your own to confirm for yourself that this is in fact true. Now that we're comfortable with this, let's take another moment to look at minus 1429 in binary again. If you naively convert this 16-bit number to decimal, you could easily think that it represents 64,107. If you like, you can take a moment to check my conversion. 64,107 is an absolutely valid interpretation of this particular series of bits. This is an inherent limitation in the way we represent integers in a digital system. Your application needs to take into account whether the number is signed or unsigned. Signed means that the most significant bit indicates whether the number is positive or negative, meaning that you have one less bit available to represent the magnitude of the number. Unsigned means that only positive numbers and 0 are possible, and the most significant bit is included in the representation of the magnitude of the number. Which one you use depends entirely on the application. For the time being, we'll just make note of this as something that we need to remember. We'll cover it in more detail later. That concludes today's discussion. To recap, today we've briefly considered the limitations of a signed magnitude method to represent negative numbers in binary. We've looked at the 2's complement method, which represents an important trade-off. It is a bit more difficult for humans to understand, but it makes things much easier for machines. We've also seen the concept of signed versus unsigned numbers, and we've noted that we'll have to consider it more carefully when the need arises. In the next video, we'll talk about addition and subtraction using 2's complement in binary numbers, and we'll see the real advantage of using 2's complement. Thank you for watching.